Okay, so we're gonna get into part 4. This is the last part for unit 4, and we'll continue non-ferrous metals. Okay, so the next non-ferrous metal that we're gonna study is the third most commonly used metal, and we call the aluminum, symbol A and then L. And then we're gonna study the alloys. Okay, so when you take a look at it, we hit iron and then we did steel, and now we're gonna do aluminum. So they look very much alike, okay? Like I tell you many times, the only difference inside making these appearances is the number of electrons in the energy shell, okay? So, so what we're trying to do today is to control the number of electrons in these atoms, okay? So you don't really have like atoms. All you have is you have the nucleus with some numbers of neutrons and protons, and then we have the electrons right outside hanging around it. That's all we need, okay? And what we're trying to do, all scientists, is to be able to control these numbers and be able to take it out and put it in, okay? So that's really difficult to do, by the way. So the more you have a hand on that, we can be able to create anything we want to do, okay? And it's also really difficult because they're very, very small, right? They're very, very small. I think in the future, maybe it's going to take like maybe 100 or 200 years later, I believe if we're going to be here, we will be able to control, alright, a lot of the atomic structure and also the properties that come with it, including any kind of atoms, right, from metals, non-metals, and gases, okay? But right now, everybody is struggling to be able to get a handle on that structure and how we can be able to manipulate it. Okay, so let's get back to aluminum. So it's a very versatile industrial material. So when you take a look at the property, you have to get all of this. They all look alike, alright? So just pay attention. When I was a student, I make a chart and then I write them down so I can see the differences between them, right? The properties and their use. Okay, so they're lightweight, and then some of them are with very, very high strength, and they're very good electrical and thermal conductivity. They also have like a very high reflectivity, okay, for heat and also light. And they have very high corrosion resistance, and that corrosion resistance can apply to many conditions like in the air or in the room, okay, outdoors and indoors. They are non-toxic, so therefore we can use it for food purposes, and they're very much costable, and some of them are heat treatable, right? So these are major properties for aluminum and its alloys. Okay, so in automobile industry, we use aluminum. So where we use it in its body, okay, body parts. So here you can see the body part. So that's looks like for Jeep, and then this is just a regular sedan. Yeah. I'm gonna go ahead and show you some codes, but you definitely need to play with the codes if you want to stay in the material line. Usually work very close with the supply chain. Okay. You go by codes for if you want to go into purchasing. You have to go around with the dealers and sit down, make deals, and buy. Okay, wholesale's kind of like that, and they have like a global trading. Okay, and they're very, very, very big businesses. And so these people use all these codes for buying and also checking the quality of the material you're buying and trading, okay? So when you take a look at the code looks like that. And we go with the 1XXX series or 2 series, 3 series. Some people don't even say XXX, okay? You go like a 4 series, 5 series, 6 series, 7, 8, and then 9. And there are some variations in calling these codes. So typically it looks like that, okay? So when you look this is like a 6061 and then T6. So that's a 6 series, okay? So when you go here, you definitely know this alloy, okay, is magnesium and silicon alloy. Yeah? So that's just alloying elements to aluminum. So you have aluminum plus magnesium plus silicon is in 6 series. Right, so the 4 digits is going to tell you the raw aluminum and then its alloy. So the first 6 is going to stand for group, right? Otherwise, according to the principle, alloying elements added. So that's what's saying here. Yeah. All you do is 6, go to the chart, take a look at it, and you're going to know the alloying elements that is added to our main metal is aluminum. Yeah. Why do we add them? Because we want to play with their properties. Either increase in strength or increase in corrosion resistance or increase in something else, okay? Conductivity. So T, the next code is T. So that's a treatment, T for treatment or temper, okay? That's a common word and that's a formal word. Usually they go to tempered outside. So T6, so we also have code for that, and it's not explained here, but that's okay. Here in this textbook, you're going to learn only 6, but that stands for the solution treated that aluminum is, okay, with magnesium and silicon in this code, and they also furnace age hardened it, okay. Furnace age hardened mean like just put on the heat, okay. Furnace mean heat. Age mean there's a certain time, okay, and we heat treat it, okay? And after heat treatment, that aluminum, magnesium, and silicon alloy becomes really hard, okay? Meaning like we're increasing the tensile strength. And that's what this code means. So let's wrap it up. So the code 6061T6, it stands for aluminum, magnesium, okay, silicon alloy, yeah, temper T, so a solution treated. It's just a method, okay, of heat treatment. And surface age hardened it. So here you can take a look at the global raw aluminum alloy right here. So they will sell you and trade you that way, and they cost a lot of money, okay, millions and millions of dollars to buy them, and then distribute to make more products out of it. Yeah. Okay, the next. So we're going to stick to this, but this table is a little bit different from the first one because see, there's a decimal. So the only difference is here we're in the cast aluminum alloy. Okay, the other one was a raw aluminum alloy, so a little bit different. So if you see the decimal between the X, right, the second and the third X, you know that we're dealing with the cast aluminum. Yep. So the first digit indicates alloy group. So we have a 1, 2, 3, 4, all the way to 9 series. So if you get 5 series, that's magnesium alloy element added to aluminum. Yeah, that's how you read it. So the second and the third is going to indicate the alloy within the group. Okay. Last digit separated by the decimal, it shows the product form. Okay. But we're not going to get into detail. If you can get the alloying element here for this textbook and this course, you're okay. So these alloy elements are added to aluminum. Yeah. And here you can see the cast aluminum. It's a little bit different, yeah. Oh yeah, the next word that they sometimes use Some companies just go with a series, and some companies like to use a designation, okay? But it's the same thing. I'll call it just code. Okay, this is a more complicated table. I'm showing you aluminum right here, and it's just explaining different series. They're not in order, okay? And here is where concentrating properties, and here is their application or use, okay? So pure aluminum in series 1, they're about like a 13 psi in strength, and they have high conductivity. We use them in wires and bus bars. The next one is we're going to age harden the aluminum and then put zinc, copper, magnesium, and make alloy. They're in 7 series here as well. Yeah? So the strength is about like a 98 ksi tensile strength. So 7 series aluminum, we use them in structural components because of their high strength alloy property and their poor formability, and they have like a very low wettability. Okay, so we use them in machine frames and truck bodies and architectural trim extrusion. Okay, series 3, 16 and 50 ksi, and they're just a general purpose alloy because they have good formability and wettability. Wettability means like you can weld on that alloy, okay? And they're corrosion resistant. So you look at the application, we use some sheet metal parts, like the cover and the shoes and guards, wire weights and switch boxes. In the 5 series aluminum, they have like the same thing, about 16 to 50 ksi. They vary by the weight and strength. They have good formability, wettability, and they also have corrosion resistance. So when you look at the use or applications, we use the 5 series aluminum alloy in storage tanks and structural members. Okay. The 6 series, they have like medium strength alloy, very good wettability, moderate formability. So they're using the 6 series in structural components, okay, machine frames and truck bodies, and the architectural extrusions. Okay, so these are the same thing. And then 2 series aluminum alloy, the same thing. They have a high strength, okay, poor formability, but you can fabricate them, yeah, and they have lower wettability. So we use them the same thing in structural components. When we say structural components, there are many different parts, okay? Like if you think about the automobile, train, or airplane, they have structural parts. Aluminum is really good because they're light, okay, lightweight. And they can also give you like medium to high strength. So therefore, we use them in structural components, okay, frames and body structures, things like that. Okay, so this is just an example for your 60626 aluminum bar. Alright, they cut it in like 1.9 meter. This is just the dimensions, and the cross section about like a 25 millimeter by 25 millimeter, and they calculate the modulus of elasticity for that aluminum, okay? And they get like about 26, okay, gigapascal. So if you take a look at it, that means, alright, they have low modulus. And modulus of elasticity is definitely not sensitive to the composition of alloying element, okay? Every time you have a composition of alloying element, they do have the modulus of elasticity because it's more about, okay, if you can stretch it or not, right, for the industrial material. So in this case, aluminum is not as stiff as steel and copper, okay? If you calculate it, you get about like 26, right, GPa, which is just sheer modulus of elasticity, okay? Meaning like it has low modulus. Okay, then we'll get into the surface of aluminum because it's very important for corrosion resistance. So look at how shiny they are. So a surface outside film, right, is what we have here for aluminum, and that is completely corrosion resistant. Okay, meaning like corrosion cannot happen on aluminum surface easily. So if you think about the indoor application, right, everybody has like aluminum foil for food wrapping or baking something in the oven. So leave it for years, it will stay shining, yeah, indoors. So that means that they can remain corrosion free for indefinite time. Okay, so that's pretty good. So corrosion resistant, again, when you think about outdoor application, so that depends on chemical and moisture condition in that environment. So corrosion rate is usually high for the first 2 years, right? But after that, aluminum surface, they become covered uniformly by an outside film, right? And that is kind of like protect the aluminum. So aluminum alloys, they're attacked by seawater, okay, and also seawater spray. So you don't want to use aluminum in contact with seawater because water carry in pipes, right? We use water all the time. We transport water because we need to use water at home everywhere. So water is carried in pipe, and that water contains metal, okay, metal ions like copper ions, tin ions, nickel. So we also add chlorine, right, to get rid of bacteria. So these ions, they cause pitting, something called pitting. If you use aluminum, right, surface can't stand pitting. So aluminum is not, we don't use in plumbing, okay? Not widely used. We use some, but the water got to be not carrying these pitting metal ions, right? So you make sure you can also check, okay, if you go home to apartment or your house, go and buy at Lowe's or Home Depot, okay? They have water, we call it the testing strip. You can buy them about like maybe $2 to $5, I think, depends on the manufacturer, and you can test your water, know like what materials, okay, what metals or what kinds of materials are in there water that you're drinking or taking shower, okay. It's better to test like every year, so that way you know what's inside, so you can choose whether you're going to drink the purified water from the store or heat the water out to get rid of these ions, okay. So pitting, it happens when corrosion penetrates into the material, right, through the localized hole. So again, aluminum cannot be able to stand pitting, and that's the reason why we're not using it in plumbing. Okay, when you take a look at the many aluminum alloys, alright, they're surface coated, most of them are, and that's for corrosion resistance. Okay, we want to increase the corrosion resistance in them. So surface coated aluminum alloys are used in decorative applications, alright, in constructions. They don't use for strength, but they're used for decorative applications. So most common aluminum surface coating, okay, when we coat aluminum surface, we use a particular method, and we call that anodizing. So anodizing is nothing, it's just it's a thick outside coating, okay, we make that by using the electrochemical process, okay. This process actually is porous, meaning like it makes a pores in the surface of the aluminum, okay. It's fast and it's good, but it makes pores. So if you immerse the anodized coating, okay, there's a D actually at the end, anodized coating, and you put it in the water, okay, it's going to convert the outside to a hydrated form. And that outside is going to swell and then reduce the pores, right, in the coat. So if you put the dye in the sealing water, right, in the sealing water, coating is going to take on that water. That's exactly how the architectural shapes and automotive trims are colored, okay? So all you gotta do is put the dye with the water, and the water is gonna go into the coating surface, all right? And then seal that pore, okay? Seal that pore size, and thereby painting the parts, okay? So that's what we use this surface coating method, anodizing, and with that method we paint some of the parts, okay? So what are we trying to do? Make the pores and then fill the pores with the water and the dye. So here we have two groups going on. One is a non-heat treatable grade and the other one is a heat treatable grade. So this group, aluminum, it cannot be hardened with heat, and that group it can be hardened with heat. Okay. So in this group we have 1 series, so that's a pure aluminum. 3 series is aluminum manganese, and some people call it 5th, okay, instead of 5. Either way, it's a 5 series. You can also call it 5th series, and that's aluminum magnesium alloys. Okay. Heat treatable, you have aluminum copper for your series 2 or second series, and aluminum silicon alloy, okay, your 4 series, aluminum magnesium silicon alloy is your 6, and then aluminum zinc is your 7, okay? So make sure you get this table. Usually just remember this site because it's easier, and the rest is gonna be that, yeah? Sometimes people put something wrong, and then usually MCQ just confuses you, yeah? But yeah, so try to get these metals, alloying elements especially. But I'm not going to be asking you more than what's in the book, okay? So just stick to the questions in the book. I might throw you out one or two. You have only 2 things to study. One is a lecture handout, and the other one is questions in your assignments, okay? So concentrate in that, and you should be okay, yeah? Alright, solution treatment. So it just, even though we say solution treatment is a heat treatment, okay? So don't think like water is in it or something like this. Anyways, a solution treatment, just a name. So we're gonna use aluminum alloy and we're gonna heat treat, yeah? And this heat is gonna dissolve the alloy elements in that aluminum, okay? So alloy elements point into the aluminum because we're heating, okay, aluminum alloy to dissolve that alloy elements they have back into the aluminum. And then we're gonna quench, okay, quench, remember, like another heat treatment. Even though it sounds so watery, both of them, but they're all heat treated. So when the alloy of aluminum with 4% copper, okay, if you heat it all the way to 930 degrees Fahrenheit, the copper is going to dissolve into the aluminum. So when the aluminum copper alloy, we're going to quench, meaning heat treat again in water, right? The copper is locked in the aluminum matrix, okay? Water just we put there to balance that heat, so you don't overshoot the temperature, yeah? So solution treatment does not increase the hardness of the aluminum alloy because there's no hardening phase formed, all right, upon heating or quenching. I want you to try to get this because I'll be asking you, please describe what's the solution treatment. So you're gonna write blah 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 blah, okay? age hardening. So if aluminum is held, we're gonna hold it at 400 degrees Fahrenheit, and it's called age because we're doing it a period of time, okay, for a time, so for several hours. And copper precipitates from solid solution, and it's going to form the CuAl2, okay, copper aluminite. So the intermetallic compound CuAl2 is a hardening phase. It's just a phase, and this definitely strengthens this aluminum alloy. Okay, so the entire process is called age hardening. Heat it to 400 degrees Fahrenheit, okay, and you're going to heat it for several hours. You will get copper precipitates, and it's going to form CuAl2. Yeah, CuAl2 is just a phase, and what it does, it makes the aluminum alloy stronger. Yeah, therefore hardening. Age means taking some hours on heat. Okay, so the final hardness and strength of the aluminum alloy, they're dependent on the size and distribution of that precipitated phase. Okay, this guy. So the age hardening process needs to be controlled. Okay, you have to control every time you use heat. We have to control, otherwise it's going to explode. Okay, we definitely need the process to be in control, and we're going to needs to be controlled in terms of temperature and also time, so we get the optimum property. Okay, so what we want, our desire, is to get the best quality. Yeah, so that's the optimum property of aluminum alloy. So you have to make sure that you're doing it right and playing it right with your temperature and time. Yeah. Annealing, another heat treat. So annealing is performed, and we perform it on cold work alloys. Okay. See, not so. It's more in control to do annealing. Okay, so we're gonna perform on cold work alloys to aid the forming. Okay, so annealing gives the casting the same structure throughout, and then it's going to make the mechanical properties even more uniform. Yeah. So that's the power of annealing, because you get the same structure throughout. Okay, even though it's so easy to say, it's really difficult to do. Okay, so you need skills in casting to do that. So annealing is done by heating the aluminum alloy to an elevated temperature or higher temperature, and then we're going to slow cool. Okay, I already told you this one previously, we studied that. So different aluminum alloy requires different annealing temperatures. Okay, because the composition of aluminum alloy is different, so therefore you have to apply different annealing temperatures. Okay, so here you can see some pictures, and here that's for aluminum 2 annealing, and this one is aluminum alloy annealing. Okay, the next method is aluminum quench hardening. Here you do the deep drawing. Involves a large deformation on an aluminum alloy. So this deep drawing, why are we doing it? Because we want to harden it. Okay. So this process usually hardens the material. So it causes hardening on the material. So sheet metal part subject to deep drawing operations. Okay, they're going to require annealing between drawing steps. The annealing is just more of a shaping, okay, so we need that. So otherwise the material is going to crack, yeah, at the strain hardened locations. I mean, strain means like if you have a stretch. okay, on some of the locations on that sheet, then it's going to crack. Yeah. So to prevent cracking, we have to do annealing, okay, between the drawing steps. So you draw, you anneal, draw, and then anneal, and then draw, and then anneal. Yeah. So what are we trying to do? We're trying to harden the material. We're trying to harden the material without cracking. Okay. Okay, now we get into the next metal. That's the titanium. Titanium and its alloys, we've been using that since 1950 in structural materials. We discovered that in 1791. That was a long time ago. But it was first time produced in the metallic form in 1910. Okay, so that's pretty new. So commercial processes were developed for its manufacture in 1940. Okay, we're going to manufacture titanium. So since then, the production processes have been improved significantly. Okay, and they got cheaper. Yeah. So 70% of titanium application or use we are in on titanium, aluminum, vanadium alloy. So it's composition of 90% titanium, 6% aluminum, and we use 4 vanadium. Yeah. That is still pretty good because you've got like about 90% titanium. So when you take a look at the property while we're using it for manufacturing is because it has high strength to weight ratio. So that means the structures can be lighter by supporting the same level of load. And they have higher modulus of elasticity, okay, unlike aluminum. Excellent high temperature properties. You can go all the way to 1020 degree Fahrenheit. And they have excellent corrosion resistance. So if you look at the pure titanium all the way to 99 to 99.5% pure titanium, you will usually see oxygen in the titanium, okay? And that oxygen can strengthen the metal. They also have lower strength titanium, okay? They have higher corrosion resistance, and they're less expensive, okay? So that's a pure titanium. So again, if you think about, they can strengthen the metal, but then they also have a lower strength. So every time you want to increase the lower strength to high strength, you're going to play with the oxygen in titanium. Okay. Since they have like very high strength to weight ratio, we use titanium in airframes. We use them in chemical plant parts because they are excellent in corrosion resistance. We are going to use them in marine parts. The same thing because the corrosion resistance is so good. We're going to use them in surgical implants. Why? Because it's lightweight, okay? Strong but lightweight. Okay, so the titanium alloys, 70% of all titanium application, okay, they use a titanium, aluminum, vanadium alloy. I already show you what's in it. Okay, 90% titanium, 6 aluminum, and 4% vanadium. So when you take a look at that alloy, the properties that easily welded, okay, easily forged because of how shine, easily machined and heat treatable, and they have good metallurgical stability, okay, strong. And where are we using? We're using in the mill products, the sheets, rods, wire, extrusions, rock and mortar, cases, blades, okay, this for aircraft turbines, pressure vessels, gas and chemical pumps, cryogenic parts, marine components, and the steam turbine blades, okay? So if you want to go into the marine industry, the shipping industry, you can also get in there because especially they're in Europe, okay, UK, okay, very, very big. And also we have US, okay, shipping industry as well. So that's another one. I'm gonna post some links for you guys to apply jobs there, okay? My father is completely from shipping industry, supply chain. um, that's another a big, source of money source. So, but I don't know why the American student don't really want to get into shipping industry. Maybe they just want to stick local. It seems like they don't want to move so much. But it's exciting, right? To go different places. Uh, think about it, okay, for your career. Okay, so heat treatable. Again, the titanium alloys, they're heat treatable, and we usually heat treat. Why? Because we want to play with the tensile strength, okay? We want to make all the way to 165 ksi. We already told you they have good metallurgical stability, and it can go all the way to 900 degrees Fahrenheit. Line elements, we add usually like that, okay? Line elements to increase the strength. So what else can we add? We can add tin, iron, and copper, okay? But this is a common alloy, titanium common alloy. You can also add tin, iron, and copper to increase the strength. So it depends on where you want to use, okay? Then we're going to get into zinc and magnesium. So zinc looks like that, magnesium looks like this. You need skills to be able to differentiate. So purchasing people in that trade, okay, but they always go with the code, okay. There are some bad business cases and they try to cheat you, all right, by putting something else, you can say. So you gotta be able to differentiate and check everything what you're getting and for what you're paying, yeah. Okay, so zinc and magnesium, so molten metal flows better if it is heated above melting temperature. So when you're making a molten liquid out of the metal, you gotta heat above the melting temperature, okay? So zinc and magnesium, they both have low melting points, right? So zinc melting point is 787.3 degrees Fahrenheit, and magnesium melting point is at 1202 degrees Fahrenheit. So therefore, they're easy to heat treat, okay? And we're gonna heat all the way up to above that melting temperature because they're very low. So therefore, you can control easily, and you can heat above them, okay, above these temperature easily, and cast them into complex shapes efficiently. So this temperature is nothing, heating industry, okay, because you can definitely control. We call them low temperature. High temperature means going all the way up to 2500, yeah. So low temperature casting requires less expensive equipment, okay. Equipment wise, even if in a heating industry, heat the metal, okay, making it molten and shape them, uh, you still have to use, okay, a lot of money, having a better, good system, right? Because you're dealing with heat, dealing with fire, okay. It's if you don't do it right in your system meaning it system composed of components, and these components are equipment, okay, that can handle many different kinds of heat treatments that we're doing on the metal to shape them. So for zinc and magnesium, right, so the heat plant in there, they use a less expensive equipment because you can handle this temperature very easily, yeah. And we can also cast them easily. So that's what this says, is that they're usually cast. Cast means making shape, okay? As you heat the metal, make it molten metal, and then you cast, yeah? So you can be able to distribute and sell them right to retail shops or constructions. Okay, zinc. So steel coated with zinc for corrosion resistance is called galvanized steel. Okay, so, I've already taught you galvanized steel. So when you think about it, it's just a steel, and we coat that steel with zinc. Okay, so zinc surface on the steel. It's called galvanized steel. And low melting point of zinc is going to allow a variety of molds, right, to be used for casting, because you can easily handle that molding or casting. They have low solidification temperature, meaning when you're casting or molding, okay, they can solidify easily. So low solidification temperature. That range is also going to allow the parts to be removed from molds sooner. Okay, so you can move the parts from the molds because they have low solidification temperature, meaning it doesn't take a long time to mold. Okay, you got the product in a short time. Okay, so if you add the zinc to aluminum, about 3.5 to 4.3% aluminum, you will get the zinc aluminum alloy. And we use that kind of alloy for casting, even though we call it zinc alloy, aluminum in it. Okay, so aluminum is going to add more strength, it's going to reduce the grain size, and it's going to minimize the attack of zinc alloy on iron and steel casting equipment. Okay, because zinc can attack the iron and steel, but if you coat with aluminum, then that attack is going to reduce. Okay, so therefore we add aluminum. Aluminum also increases the fluidity, alright, of molten zinc. So meaning like if you heat the zinc aluminum alloy, this alloy, the fluidity is pretty good, so you can cast easily. Okay. If you add about 5% of aluminum, alright, more than that range, you're gonna get zinc aluminum alloy. But then that kind of alloy, it turns brittle, right? Meaning it can breaks easily. Okay, general properties of zinc alloy. They have excellent atmosphere corrosion resistance. They can adhere well on substrate. Okay, they have high castability. They're easy to finish. They have good mechanical properties, and they are definitely free of intergranular corrosion. So if I ask you what's intergranular corrosion, you should be able to write it, okay, in your exam midterm. So make sure you get on with that process. I think I might give you a study guide, okay, so you know what to study. So that would be great, I guess. I'll do that this weekend. Okay, use is going to be protective coating for steels. It's about 52% of zinc alloy. Okay, to make galvanized steel, we use about 23% in die casting operations. Alright, types of molds. The mold types, we use plaster molds, we use metal molds, we use graphite molds, and we use silicone rubber molds. Okay. Alright, the next metal we're going to study is magnesium, Mg. You can find magnesium in large quantities in seawater. Okay, so the strength is about 27 ksi at room temperature, and that's not enough for structural use. So you have to make it alloy, yeah, with other elements to increase that strength. So we're going to add aluminum. So we get magnesium aluminum alloy. So that increases strength, castability, and corrosion resistance. And we're going to add zinc to aluminum and magnesium, and you get magnesium aluminum zinc alloy. It's very lightweight, it has strength, and it is corrosion resistant. So the use, generally we use magnesium and its alloy in aircraft, okay, parts, missile parts, machinery, tools, material handling equipment, automobile parts, computer parts, die casting, automobile wheel in your car, lawn mowers, business machines, chainsaws, the hand tools, and the sporting goods. Okay, various sporting goods. Property, when you take a look at it, they have lightest structural metals. Okay, they are lightest structural metals, but they're difficult to plastically deform at room temperature. They're lightweight. They have superior ductility. You mean like that you can draw them. They have excellent machinability. They are reasonably corrosion resistant, and they burn extremely hot, right, if ignited. So you have to be very careful. So here is your caution. So water cannot put out the magnesium burn or magnesium fire, right? If they burn, it's very hot. So therefore you don't want it to get ignited because you can't use water to put it out. Yeah. So you have to use something called flood coolant. Okay. You have to apply that in machining and grinding operations, okay, with the magnesium alloy to prevent that ignition, okay. Make sure you get this point for midterm. Okay, then we get into the last part of the metals, non-ferrous metals, is your precious metals. So they are high cost, okay, you have to pay a lot of money to get these metals. We have three. One of them is platinum, and second silver and gold, okay. That's platinum, that's this is silver, and then that's gold. Yeah. So we use it in jewelry, coins, and bullion. Okay. We also use automobile, the catalytic converter. Yeah, catalytic converters are expensive. And don't break down your car and take it to maintenance every 3,000 to 5,000 miles. Okay, depends on your car manual, please. Okay, let's get into platinum. So primarily we use platinum in industry for corrosion resistance, okay? So platinum alloys are only material that can be exposed in air all the way to a temperature of about 25-50 degrees Fahrenheit. So this is their special use, okay? And pretty good. So the general property, resistance to nitric acid, condition at all temperature and concentration, resistant to sulfuric acid at most temperature and pressure, highly resistant to hydrogen fluoride and most fluoride compounds at very high temperatures, resistant to sulfur dioxide, slightly resistant to hydrogen sulfide, okay? Or resistant to chlorine at high temperature above 212 degrees Fahrenheit, okay? So what are we using? Platinum. So in platinum alloy, we use them in production of optical glass, okay? Production of high purity glass like this, lining of melting furnaces, and pouring gates, acid storage vessels because they are resistant to most acids. Production of organic fluorine compounds, okay? Because they are resistant to hydrogen fluoride and most fluoride compounds, okay? Highly resistant, so therefore you use them in production of organic fluorine compounds, production of large synthetic optical crystals, okay, from molten lithium fluoride, and then from molten sodium fluoride, okay? For everything to do with fluoride that you want to handle, we're going to use a platinum alloy because we can hold them because we're resistant to it, yeah? The platinums are resistant to it. So here is your platinum rock right there. Silver, your symbol is Ag, and we use them in electrical contacts like that. So those are not buttons, alright, those are silver electrical contacts. So largest use in photographic emulsions. Second largest use in electrical and electronic applications. Okay, this is under that. I can move it a little bit because okay, highest thermal and electrical conductivity among metals is silver, and they have a slightly higher conductivity than pure copper, but they have much higher conductivity than gold. Okay, so silver is very good for thermal and electrical conductivity. So when you look at the general properties, you see the high electrical conductivity, high resistance to oxidation, arc erosion resistant. It does not easily oxidize, okay, at room temperature. We use the silver in electrical contacts, okay, medium and high current voltage applications, relays, timers, thermostats. And we use in limits and pressure switches. We use in fractional horsepower motor start switches. And we use it in metallizing non-conducting materials. Okay. Silver-based electrical contact alloys. We have 3 of them to make silver-based electrical contact. So these alloys are silver cadmium oxide, silver nickel, silver tungsten composites. So these are your alloying elements. So we're adding cadmium oxide into silver, okay? Nickel into silver, tungsten into silver, okay? Alright, we're going to continue silver. Alkaline cyanide in air or other oxidizing agents, they can dissolve silver. So nitric acids, okay, that contain traces of nitrous acid, these can attack silver vigorously. Hot concentrated sulfuric acid, hot disulfuric acid, and sulfur dioxide can also attack silver or silver-based composites. General property, they're high corrosion resistant, they have high product purity. So where we using silver, we use it in chemical and food processing equipment, we use it in solid sheet, tubular form, we use it in lining over copper, nickel, carbon steel plates. We use as liner in heavy duty bearings, okay? We use in applications with halogen and halogen acids. As handling wet chlorine gas in water purification installation, you have to do it with silver, okay? Use it in control and metering equipment and tubing. We use it in application with aqueous hydrochloric acid, pressure vessels, and process equipment, okay? They also use silver. Okay, now we're gonna get into gold. The symbol is AU. So before 1950, gold was used as monetary. So after 1950, gold is used by manufacturers and investors. And gold and silicon, they can form a low melting compound, okay, which is bound to semiconductor to its base. So here you can use the semiconductors right here. These are gold semiconductors. So you have gold trims and semiconductors. General properties. So gold is oxidation resistant. It is resistant to corrosion, and it is resistant to tarnishing. Okay. So what we use in jewelry, dental uses like gold teeth and silver teeth, things like that. Sensitive light filters, thermal limit fuses, targets, and X-ray equipment. We use in freezing point standard, okay. High melting solder. We use in vacuum type pressure welds. We use linings for chemical equipment. We use contact springs in radio frequency circuits. This is important. We use gold like silver in electrical contacts, telecommunication equipment, and those are actually electrical contacts. Okay, this is semiconductor. We also use in surface films, silicon transistors, integrated circuit chips, and electrical terminals. Right? Okay. That's it for this big chapter, Unit 3. Unit 4. So we have ferrous for Unit 4, Part 1 and 2. Then we have this Nonferrous, Unit 3 and 4. Sorry, Unit 4, Part 3 and 4. Sorry, somebody's in the back distracting me. So, this is the annual offers cutoff. Unit 1, 2, 3, and 4, please study. And that's for your midterm exam. I'll try to post a study guide for you, but literally they're all the same, right? So if you hit the assignments, questions, then you should be okay. Alright, that's it for now.